All right, everybody, welcome on in. So, a couple things. So, notice you've got some homeworks and some lessons due tomorrow. So, some of you are on pace to have that turned in, some of you are not. You can still work on it afterwards, but you only get half credit. So, make sure that you're getting that stuff taken care of and that you're, moving things along. It's a shortened course, so we got to move a little bit faster, and you definitely don't want to get behind in that stuff. Okay, so let's see, and then you have a little bit of time to turn in the project part related to this, but I would just do it now, right? Because if you think about 2 weeks from now, how much, or 2.5 weeks from now, you're going to be you're going to forget some of this stuff. If you just do it now while it's fresh in your brain, then you're good to go. So last time we talked about the survey. So I released the results for the survey. You can start working on your projects. You can start turning in those assignments. Okay, so make sure you're doing that. Make sure you're doing all of these, right? You get points for them, and they go towards your project grade. And they're basically these ones. I don't grade very hard because you're just learning the stuff, and it's just starting to make sense to you. So, basically, if you get in there and you do an honest effort to try to apply the statistics in a way that, obviously looks like you put in some effort, then I'm going to give you credit for these. So that's a nice way to pad that project grade by getting the points now. Plus, it makes it easier later when you're trying to put your project together. You've done a bunch of the work. Now, remember, when you get full credit on these, that doesn't mean you did an A job. It just means that I'm saying, okay, you went in there and you're sort of you just learned this material and you're getting the hang of it. But by the time you do the project at the end, then I have a little bit higher level of expectation because you've had some time for these ideas to sink in, connect with other ideas in the class, and make sense of it. Just because you're getting 10s on these doesn't mean you're going to get 100% on the project, right? Just be aware of that. It's just that I'm motivating you to get some of the work done along the way. So you have Chapter 3 due. Oh, wait. Chapter 3 was due a couple days ago. Chapter 4 is due tomorrow. And then make sure you're doing these project pieces on the end. You can always come to office hours and check with me before these are due and say, hey, here's what I did. I'm not sure if I really did it right. And I look it over. I do that with students all the time, and it turns out pretty well for them. So, basically they get the answers that they need and they understand what they're doing. So their stuff is improved generally. So that's what we've done for the last week. And then anyone who wasn't here last time, we spent basically the whole time I spent showing you how to do work from the project. So make sure that you're watching those videos, right? And I realize you're either here, or if you're not watching the video, you're not hearing me say this, but if you're not sure what to do with the video or with the project, I spent a whole video showing you how to go into StatCrunch and how to change your data to make it better and how to do the different stuff, and talked about expectations in the project and all that. So go back and watch that, and then you'll learn some about how to do the project. Speaking of which, we've got this part with the correlation. Actually, before we get into that, let's learn a couple new topics. So we were talking about correlation. Remember, correlation means a connection between two variables. It does not mean cause and effect. It is so hard to fight that. Our brains and the way we're brought up in society and the way our brains are just structured biologically, we are trained to automatically think that if two things are related, one is causing the other, right? But in statistics, you're always fighting that. A does not necessarily cause B, right? Ice cream consumption does not cause shark attacks. However, those two variables are very closely related. So we really want to be careful about that. And that's a big one on their project. If you are talking about one thing causing another, it's probably going to lead to you getting deductions on your scores because you've sort of missed one of the major points of this class, which is the tools we develop in this class are almost never A causes B, right? It's much more complicated than that, just like things in life, right? A lot of things that we do in society, politics and all this kind of difficult stuff that we're trying to tackle is never just one thing causes this other thing. If it was, it'd be easy to fix. It'd be easy to go in and fix all the problems that are sort of facing society today, but it's not, because they're caused by lots of things. So it takes a much more nuanced, and it takes a lot more effort to look at these problems and figure out what the actual solutions are, not just little sound bites that we hear from our politicians, but actually going in and trying to make meaningful change, and really, whether it's your business or research or politics you're into, trying to make that meaningful change takes a lot more looking at and inspection than just, an A causes B situation, because that almost never happens. All right, so we talked about that last time. So now we're getting to this new thing, regression. So we talked about correlation. Correlation, right? We say two variables are correlated to each other. That means that they are associated in some way. You can have a strong correlation, which says that two things are closely related: ice cream consumption and shark attacks. Those are closely related. One doesn't cause the other, but they are closely related. Two things that I would guess not closely related: ice cream consumption and height, right? Maybe, because I guess kids eat more ice cream, but sort of say you take adults, once somebody's like, say, 20, I doubt your height really has much input on your ice cream consumption, right? So, sometimes things are closely related, sometimes they're not. That's correlation, right? Oh, and one thing, I got a question in office hours yesterday. I don't remember if it was someone in this class or the other class, but I wanted to make it clear because I think that person was confused. And reasonably so, very reasonably so, because it's a very common way to think about this, is they were thinking that a correlation is really only important or worthy of talking about when you have a strong correlation, either strong positive correlation or strong negative correlation. However, proving that two variables have nothing to do with each other is also an interesting thing to figure out, right? So you might have gone into this project, one of your questions may have been, how many hours do you spend working per week? And another question may have been, how many units are you taking this semester? And thinking that the number of hours worked would have a correlation with the number of units that you're taking, right? That's a reasonable hypothesis. I think that the people that work more might be taking less units because they're spending their time working. That's a reasonable hypothesis. I've also heard it the other way. I think that people who work more are also taking more units because they have to make more money to pay for school, right? As I've actually heard both. So let's say that was your hypothesis and you went to study it and you found a very low correlation between, and I'm just making these values up, so this is a hypothetical situation, but you found a correlation, an R value near 0 for number of hours worked and number of units taken, and you say, oh, darn it, there isn't a strong correlation here. That doesn't mean don't talk about it, because that's actually information. If I'm sitting here wondering, is the number of units taken connected to the number of hours worked? And you say, no, our data shows that there is not a connection between these two variables. We just learned something, right? We now understand the lives of our students a little bit better, because we can now confirm that, or with a certain level of confidence, that the number of hours worked per week does not relate to the number of units taken. And again, I'm just making up these outcomes. I don't know if there was how those two questions relate to each other. But that's my point. Is I think there's a tendency for people to think you should only talk about correlation when it's a strong correlation, but also it's interesting to find out two things are not related, right? Because then not to go down that whole path of trying to figure out, why are these two things related? Well, they're not. Oh, okay. Well, then I guess I guess we won't go down that path and try to connect those two variables, right? So even if you only ask two numerical questions and you find that they are not correlated, that's worth discussing. That's worth saying, this thing here, the number of hours worked, does not seem to impact the number of units taken. Okay, I now understand something a little bit better. Right? But there's this bias where people think it's only if you can prove a positive result that it's valuable. Nah, even proving a negative result or showing evidence for a negative result can be helpful. Okay, so what is regression? Looks like I can make this a little bigger here for the screen. So given a collection of paired sample data, and you have that because this is what you did. You remember I recommended when you pick your questions that you have two numerical questions. Well, those are paired by people. So each person answered your first numerical question, and then they also answered the second numerical question. So we say that they are paired. They are matched up because even though you don't know who it was in the class, you can say, this person here said they work 35 hours a week, and they're taking 10 units. This person here works 20 hours a week, and they're taking 9 units, right? So they're paired because you can see it's not like two random lists where we can't match up who said what. We can match up the outcomes from both outcomes from one individual. That's paired data. They've been paired together. Okay, so, and if you think about it for a minute, it gives us more information than if we just had here. In one survey, I asked people how many hours they work, and then in a second survey, I asked people how many units they were taking. Well, that doesn't do me any good because I can't tell who said what. But if we have one person who said, I work 20 hours a week, I'm taking eight units, then we know those things are connected. They are paired together, okay? So what we want to do is come up with a regression line. And this regression line is known by numerous names: a regression line, a line of best fit, a least squares line of regression. There's like a million different variations they call it. It all means exactly the same way. It means this equation right here. Now this might look weird because there's new symbols and stuff that you're not used to, but you know this equation right here, right? Many of you can say it, but you may not remember how to use it. It's y equals mx plus b is all this is, right? Except in statistics, they want to do it a little bit differently, so they write it different. This would be the same as y equals b plus mx. So notice they're even using b, but our m would be this b1, the coefficient on m. So that's helpful. What does this mean? Well, remember before when we looked at these graphs of data? Let's see, where was that? Right here, we have these different types. You go through, you make a scatter plot on StatCrunch, and we see different behavior of the data. Here I see the overall behavior is moving up and to the right, but kind of in a really spread out way. That data is not really tight. It's kind of loose here, right? Here we're moving right and down, but this data is a little tighter. It's clumped up a little tighter than we had over here, right? And notice that the R value is closer to the extremes on the end, whereas this one's a little closer inside. You still get a decent correlation here, but it's not as strong as this one over here. All right, this one's almost at -1. Okay. Here, your R value is 0, and you see, if you wanted to draw a line through this data, there's a million different lines we could draw that you could argue. Like here, it's obvious. You're going to start somewhere up here. You're going to draw a line to somewhere down here. StatCrunch will do the exactness for you, the exact line that goes through here. But you can kind of visualize a line running through here, right? Here, where would your line go through? I don't know, right through the middle, maybe up this way, down there, who knows? And here, there's no great place to put a line either, right? So that's what we're looking at, is a line that goes through the data that gives us an indication of the overall behavior of our data. It also allows us to make predictions, which is really helpful. Right? Now, your predictions are not going to be perfect, but they're going to be in the neighborhood of the right thing. So let's go back to where we were. In fact, let's go here. Oops, that's too big, I think. Okay, so all this is y equals b plus mx. They're just switching the terms around and using different symbols because statisticians want to have their own special thing. But don't worry about that. This is basically just the line y equals mx plus b. Let's remember back to y equals mx plus b. What was the m and what was the b? The m was your rate of change. It was your slope. If you think about it, if we have a line that is describing our data, and it has a specific rate of change, that's telling us how we can expect our data to change over time if we came up with new values. That means we can make predictions which will be approximate. They won't be perfect, but they will give us an approximate guess of, and then we wanted to make and then we scatter plotted it and created a regression line, and then we wanted to predict, well, we found a shoe size at a crime scene, and we want to estimate this person's height. Well, we could use this line to estimate, well, we know their shoe size, what's their height, and then we could estimate within a given range what we think there's a high probability of this suspect's height being. Okay, so it won't be perfect, right? You're probably, you get a prediction back from your model that says 5.8. Well, the person could be between 5.7 and 5.9, right? Somewhere in there. They could be significantly taller, but the further you get away from that prediction, the less likely it is. Those are some concepts we'll build in the coming weeks. Okay, so what am I talking about? Let's look at some examples. So here's some examples. See how you have the scatter plot, and now we have a line going through it? Well, this line is not doing a great job of representing this data, right? In fact, the further away, these data points are getting farther and farther away. That usually is an indication that we are not dealing with something that is a good R value. In fact, here they're doing shoe size versus height, right? So right, so here's where they went through and they had a small n. There's only, 5 data values. Here they came up with much more. That's one of the things that's really important. The higher your sample size, the better your model's going to be. And that's why I was really trying to get more people to take the survey. We couldn't get it. I'm going to have to change the way I present that survey in the future so that people actually understand that it's important to take it. But that's for a different class to have to deal with. The higher your n is, the more accurate you're going to be able to tell if there is a strong correlation, and if there is, what your line of regression should be, right? So notice for this one where we got more people submitting answers, we got an R value of 8.13. That's kind of right in that zone where you're like, well, there's kind of a strong correlation, but maybe not. It's kind of hard to tell if you really want to put your faith in this. And you can tell if you use this to make a prediction about, say, right here at 33. So if your shoe print length is 33 centimeters, you go up. There's no data point there, but there is this line. So if we find the Y value for an X value of 33, we find the Y value, it's going to give us the point on this line, which is a good prediction for the height of the individual that left that shoe print length. Doesn't guarantee that we're going to hit their height spot on, but again, if this predicts a height of 5'7" and the suspect that you have is 5'8", you go, well, it's kind of, it's not proof, but it's kind of indicating that maybe this person has the right height for the shoe size. Okay. Right. We've got outliers. So in a scatter plot, an outlier is a point lying far away from the other data points. A single outlier can significantly throw off your regression line. So sometimes if you have an outlier that's way far from everything else, you will either mention, we're removing this point because we think this outlier is problematic for this reason, right? You don't just hide data. You're not allowed to do that. You can't just cut out data. If you do, you have to give an explanation for why you do it. Otherwise, you're being, it's considered unethical to just change your data. Otherwise, statistics is just a bunch of people lying to each other, right? So, but you can say, we think this outlier should not be considered for these reasons. And then you're being honest with whoever's looking at your work, and they can decide if they think that your reasons for removing that outlier were good or not, right? Paired sample data may include one or more influential points, which are points that strongly affect the graph of the regression line. So outliers are influential points. One outlier can completely tilt your line. So it goes from being a good model to now it's all messed up. And a lot of times you'll be able to tell just by looking, right? You look at the thing. So for instance, here's an example, right? We saw this. This is a good model, but not a great model, but it's decent. It'll work for us. And then look, we put in one outlier. So this person has size 35 centimeter length shoe print, but is very short compared to the rest of the people in this. And look how much it changed that line. This line is now, it went from a positive slope to a negative slope. So big change just because this one point so far out there, it's pulling this whole line down. So you may say, it may be that you look into, this is a good example of when you see an outlier, you want to ask why. So you look at this point and then you find out, oh, this one individual has a specific medical condition or something like that. So that's why it's skewing our data. So then you might say in your work, well, this one individual had a specific medical condition, and so we are going to eliminate that since it's throwing off our data so significantly. We don't think that this model now represents the general population, so we are going to eliminate that point. And then the people reading it know that you're not just changing data to fit what you want. It's, oh, there's a reason to believe there may be a good reason to remove this data. Otherwise, you can just make your data say whatever you want, right? And this is actually done, unfortunately, regularly, where people go in, the data doesn't fit what they want it to say, so they just change the data. That is unethical, and it is, I mean, it's lying, right? If you say, well, here's what my data shows, and the data is, that's what it shows after you changed your data to be other stuff, then you're lying. Okay, there's an idea that goes along with this called a residual. So what is a residual? These are kind of weird. A residual is, say here's our regression line. So these blue points are our actual data points. And then this blue line is our regression line, the line of best fit. Well, most of the points don't lie right on that regression line, right? There's a little bit of distance there. It's like an error. We call that a residual. Okay, the residual is that distance between a point and the actual line. But like if you plot, shoe size versus height, you're never going to get everyone on exactly a straight line, because you can have two people with different shoe size that are exactly the same height. You can have two people that are exactly the same height with different shoe size, right? So there's going to be a little bit of variation. If everything was so perfect that it all fell exactly on a line, then we're just doing algebra. You don't even need statistics at that point, right? Just do some algebra. So that's why we need this. So when they start talking about residuals, this is what they're talking about: the difference between the expected predicted value, which is on your line of regression, and then the actual data values. And those get used in the calculation of the line of regression. Now, you don't have to calculate any by hand. I'm going to show you how to do it in StatCrunch, but they're helpful to understand what's going on. Again, you should, whenever you use formulas or software to do math for you, you got to understand what those things are actually doing. Otherwise, you're just pushing buttons on a computer. You don't actually know what you're doing, right? So why are these written as squares? It's because in the calculation for line of best fit, they take the residuals and they square them. Now, why are they doing that? Well, it turns out if you have a line of best fit and then you go through and you add up all the residuals, you get 0. But that's not helpful to us, right? So what they do is they square the numbers so that they're all positive, and then that way when you add them up, they don't all cancel each other out. So just so you know, that's what's going on. It has to do with making the formulas work properly. Definition: a straight line satisfies the least squares property if the sum of the squares of the residuals is the smallest sum possible. So basically what the computer is doing, and I'm dumbing this down kind of a lot, so and I'm not saying anyone involved here is dumb. I'm just saying, like, I'm oversimplifying the concept here in order to sort of make it understandable, which is that when we find the line of best fit, what the computer is doing is it's calculating all these, like it's taking the line that would go through and reduce all these residuals. So it's minimizing the area of these squares down as small as possible, and then it's giving you the line that does that. Okay? It's giving you that line. So and then you can plot the residuals if you want. One reason we plot the residuals is if you can see a pattern in your residual, like here, we can go, oh, well, the data goes below, and then it goes up, and then it goes down again. Or here, where we can see a pattern where it's bouncing back and forth and getting bigger and bigger and bigger. That means that you probably shouldn't be using a linear regression. It's probably not linear. It's probably quadratic or exponential or something like that, right? So here's your steps when you want to do this. So you construct a scatter plot and verify that the pattern of the points is approximately a straight line pattern with outliers. Think of those 4 graphs I keep going back to. We could tell which ones were approximately linear. Okay. If there are outliers, consider their effects by comparing results that include the outliers and don't include them. So if you have an outlier and you think, maybe I shouldn't use this, just do it both ways, with the outlier and without the outlier, and see what your results are. Construct a residual plot and verify there's no pattern, and also verify that the residual plot does not become thicker or thinner. You may or may not actually do that step. Use a histogram and or normal quantile plot to confirm the values of the residuals have a distribution that is approximately normal. We probably won't do that either. Actually, this is a different list than I thought I was looking at. Where's the thing I'm looking for? Maybe it's in the next section. Rank correlation. No, that's not the one we want to do. Okay, let's take a look at things in StatCrunch a little bit. So I'm going to make up some values here. So we'll say shoe size, and then we'll go height. Okay, now we're just going to limit this to, this is obviously a hypothetical situation, but if you're doing this in real life, you would probably want to separate people into different groups, right? You probably would not want children in the same study as adults, because children grow at different rates than adults. There's all sorts of variation you're going to get with children. So you might want to just do adults, and then probably you would want to compare, you would have a group of men's heights versus shoe size, and then women, you'd probably want to separate them because there's differences in heights and shoe size between men and women. So you wouldn't do those all together. It would get really, your data would get really confused, right? Plus, most clothes and shoes are measured differently for women than they are for men. So there's that. So let's look at some shoe sizes here. Let's see, like 8.5, 9.5, say 10, 11. Oops. Okay, so say we go to a stats class. We get all the men in the class to tell us their shoe size, and then we're going to look at their height. We want to do, in fact, let's make this height. Height in inches. And really, if I was doing this, I should also do, let's see, men. Let's do male shoe size as measured in the U.S. Because if you're, and then notice when you go to the edge of the cell, you can drag it open if you want to see a little bit more of the title, right? So this is shoe sizes of males as measured in the U.S. Europe measures them differently. Lots of different places measure them differently. Okay, height in inches. Let's see. Let's make up some values here. Okay, so I've got some data here. I've got my shoe size and my height. So I want to use StatCrunch to make a regression line for this. So I'm going to go up to stats, and I'm going to come on down to regression. Excuse me. Come down to regression. Now remember, we kept looking at graphs and asking, we can see there is a behavior to this data, but is it linear? Those of you who go on to become statisticians, you'll study other types of regressions. But in this class, we're really just concerned with linear regressions. There's polynomial and logistic and exponential and logarithmic and all sorts of different regressions you can do. The ones we're concerned with in this class are just simple lines. In fact, most of the regressions that you do in the real world will be linear regressions, right? Those are, I don't know what percentages it is, but the majority of regressions done in real life will be linear regressions. You might get polynomial depending on what you're studying. So I'm going to do simple linear, and it gives me my menu. Now, I have two variables, shoe size and height. Which one do I want to be my x variable, and which one do I want to be my y variable? Well, it kind of depends on what you're trying to do. If you were trying to use this data to predict the height of a given shoe size, then we would choose x as the independent variable because we are going to input the shoe size. And then height would be the y variable. There are plenty of cases where you could switch those around and do it the other way, where x was the height and y was the shoe size. But you'd have to either way you do it, you want to make sure you're interpreting all parts of the problem consistently, right? If part of the time you treat x as you treat your shoe size as x, and then part of the time you treat shoe size as y, it's just going to get all confused. Okay. So let's just say male shoe size x, height is y. And of course you could do this for females too. It just you'd have a different group, right? Because you don't want the two together get confusing. Doing adult males shoe size study, perfectly reasonable. Adult female shoe size, perfectly reasonable. Combining those together is just going to get confused because you essentially have two different groups that have different behaviors inherent to them. So you'd want to separate those out. What is this hypothesis test and this stuff? That's I think hypothesis test, if I remember right, is the very last chapter we do. So you don't know how to do that yet. You'll come back here in a month, and then you'll be able to use this hypothesis test. But for now, just ignore it. Also, you could do a confidence interval. What's that? We haven't learned that either. That's like the second to the last chapter or something. I forget which one's the last chapter and which one's second to the last. But you will understand these later. For now, just ignore them. All right. What if we wanted to make a prediction here? Right? And we go, we're investigating a crime scene, and we want a prediction for what someone's shoe size who will be 10.5. We want to know. And what's this level? That goes back to these confidence intervals we're going to learn about. See where it says level 0.95 there? Basically, what that translates to is we want to be 95% sure about the range of values for the height. Right? We want to know with 95% certainty that we have the right height to go along with that. Don't need to do these. If you want to get fancy, you can mess with this other stuff. That's kind of up to how fancy you want to get. Always label your graph. So x-axis label is what? U.S. men's shoe size. See how I'm labeling it? And then my y-axis label will be height in inches. Remember, your goal when you create a visual for your data is no one should have to ask you any questions. I shouldn't see your data and ask, well, what was Q17? Right? If you do that, basically your visual is kind of useless, right? Because what's the point? So here we are going to do shoe size versus height. Now notice in my title, I'm not putting units. Why not? Because my units are already in my axis labels. So I don't have to repeat that again. We go, oh, this is, in fact, we could say this is, we could be specific and say shoe size versus height, male. So we know, oh, this isn't the female group. This is the male group, right? And it's all in there. If I want to know the shoe size, oh, it's U.S. So U.S. shoe sizes, height, oh, that's in inches. And here's what we're looking at. We're just comparing the two things. Right? And then I think we got everything we need to do. So I hit compute. Okay, now some people get confused here because they're like, wait, I thought I was going to see a scatter plot and a regression line. Well, notice how up here, how it says 1 of 2. And down here, there's a little arrow to go over. Oh, there it is. There's our data and our line right there. But there's a lot of important stuff on this first page. They've told us what our dependent variable is, our independent variable. Basically, we chose them, but it's reminding us. And then what is this right here? That's your regression line. You go, wait, why aren't there like X's and Y's in it? Because they're using the actual data value that we gave them, which is shoe size and height. So in other words, there's this value on our shoe size. That's our slope. Here's our the y-intercept, right? So it's kind of like how, that would be the typical height of someone when they're kind of leaving the child sizes and then they enter into adult sizes to start getting measured. They kind of would start here, right? So we've got our sample size, our R value. Our R value is pretty low. That's a pretty low R value. And again, I just made up these sizes, right? This is all just made up data to show you. But this is not a good R value. This would indicate to us that any predictions we make using this model will be bad. And this is a thing that people miss, especially when they just start memorizing all these pieces, is they're like, yeah, I've got my shoe size and I've got my height equation. Great, I can just predict the height of males given their shoe size. No, this R value says, yeah, you can use this equation. If you plug it in, the computer's going to give you an answer, but you shouldn't believe it because this R value is really low, which means that there's a lot of variation that doesn't seem to be connected to the relationship between these two variables. So you can use this, right? I find that there's always a group of students, there's a percentage of students in a stats class that if the computer or calculator shows them a number, they just have total faith in it. They just believe it. It came from a computer, so it must be right. But no, this is saying, yeah, you can use this equation, but it's not so reliable, is what this R value is sort of indicating to us, right? Don't put too much faith in it. It might be helpful, but don't put someone in prison because of this evidence right here, because it's not very good. Okay, and we can see our predicted value down here. Remember, I put in an X value of 10.5. All it's doing is taking 10.5 and plugging it into our equation and giving us the predicted Y value would be 69.655. So, okay, we found a shoe print for a person whose shoe size was 10.5. Their predicted height in inches is 69.65. Now, is that going to be right on? No. So we get into here's a 95% confidence interval. So what that means is we can be 95% confident, according to my data, that the true height of the individual is between 68.77 and 70.53. That's a concept that you're going to start to become familiar with, is we create an interval and we say we are 95% confident that the value falls within here. So if we go to our suspect and their height is in this range, we go, it's not conclusive evidence. You're not going to convict somebody on this, but it is matching the suspect that we think their height is in this range, and it is, right? If we come in and check and someone's height is significantly taller and they're outside this range, that might be evidence that, like, oh, this doesn't prove they're innocent or that they're not guilty, but also like maybe, maybe they didn't do it. Who knows? Right? And then you have, this, you definitely should include a couple of these. I do see scatter plots sometimes on the project sometimes that don't have that regression line in it, and I kind of wonder why. Was it because they didn't understand how to do the graph, in which case they should have gone back and figured out how to do it? Even if you have a regression line and it's bad, like you have a low correlation, just throw it in there and talk about it and say, here's our regression line, and look, it's not great, right? Like it kind of describes the overall behavior, but look, there's all these points that are way far away from the line. It's not like those early ones we looked at. Remember up here, where like these? Like here, it's very obvious where the line should go. Here, it's less obvious. I would say in what we're looking at here, not so obvious. Like if I gave you this scatter plot and I didn't give you the line, I think we'd come up with a number of different lines. Some people would start here and go like this, or you could come up like that. There'd be a number of different lines. It's not obvious where the line should go. That matches up with our low R value. The R value is too low to tell us that we should put a whole lot of faith in this, but also just looking at it. Yeah, that's not a great line. There's a lot of variability outside of that line of regression. So you got to be careful. But notice we've got everything labeled: height, inches, U.S. men's shoe size. We've got a title: shoe size versus height. Oh, I understand everything that's going on here. I don't have to ask you any questions about what does this right line represent. Well, it's pretty obvious. Here's men's shoe size. Here's height. And I don't have to go height, but how did you measure height? Oh, it says right here, you measured it in inches. Oh, okay. Well, there we go. Questions are answered before I can even ask them, right? So that's what you want to be doing. Oh, time's flying by when we're talking about this stuff. So I forget how to do this sometimes because I forget where this is located in StatCrunch. So if you do, again, just go to YouTube and Google, or go to YouTube and search in the YouTube search StatCrunch regression. And there's literally, you'll find little 2-3 minute videos that show you, oh yeah, you go to stat, you go down to regression, go to simple linear, fill in your stuff, hit compute, and you're good to go. Okay? So that's what you want to be doing. That's the whole reason that I made sure, I strongly recommended that you have at least 2 quantitative questions, is so you can do exactly what I just showed you to do. You can create that scatter plot with a regression line. You can talk about the R value, and you can say, yeah, we have a very reliable linear regression, or here's our linear regression. We can see it's not really very good, right? It doesn't mean you did something wrong. It just means it's not going to be good at predicting values. It's not going to be good at predicting unknown values. So talk about it, right? And again, some people go, well, I shouldn't use a regression if it's not a good one. Sure, throw it in there, because then that leads to your case that those variables are not closely related, which again, people sometimes think, oh, if they're not related, there's nothing to talk about. No, totally talk about it. Okay. Talk about that regression. Okay, let's see. Got a few more minutes. Let's go back to, I guess we kind of covered all of that. Is there any questions on anything I've covered here? You've got your contingency tables and stuff. If you have trouble with that, come see me in office hours. And then we'll start probability next week. Okay? So as always, when we end class, there's really nothing more I can say in 4 minutes that will be helpful. So make sure you get those assignments in that are due. Make sure you're working on the project. You do not want to be doing the project just all of it in the last week, because first of all, you'll miss all these points along the way, which is going to hurt your grade. Plus, your project will not be as good as the people who have been working on it. And then we'll get into stuff next week. Yep, so get those assignments. Make sure you're working on that stuff. Come ask me questions in office hours if you have questions and you need some help. Otherwise, you can come talk to me in Zoom right now. Even though I don't have office hours, I'll stick around if anyone wants to talk to me for a few minutes and help answer some questions for you. Otherwise, I will see you next week.